Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ludwig Boltzmann's 1875 paper on the relation between the second law of thermodynamics and probability calculations regarding the conditions for thermal equilibrium occupies a pivotal position in the history of physics, marking a significant step towards the statistical interpretation of thermodynamics. This essay undertakes a detailed, section-by-section examination of Boltzmann's work, critically assessing its claims, methodology, and underlying assumptions. It explores the evolution of Boltzmann's thought, the context of his intellectual milieu, and the enduring impact of his probabilistic approach to understanding the macroscopic behavior of physical systems. This analysis avoids retrospective application of current knowledge, instead focusing on a close reading of arguments found within the text itself. Section 1: Introduction and the Problem of Irreversibility. Boltzmann begins his paper by addressing a fundamental challenge to classical mechanics: the apparent contradiction between the irreversibility of microscopic laws and the observed irreversibility of macroscopic processes, as encapsulated by the second law of thermodynamics. He acknowledges the prevalent view, championed by figures such as Clausius, that entropy, a measure of disorder, invariably increases in a closed system. Boltzmann seeks to reconcile this with the deterministic nature of Newtonian mechanics, where every process is in principle reversible. This section lays the groundwork for his subsequent probabilistic argument, highlighting the need to move beyond purely mechanical descriptions to account for the statistical behavior of large ensembles of particles. The introduction is valuable for establishing the central puzzle Boltzmann attempts to resolve, specifically the arrow of time and its relationship to microscopic dynamics. Evaluation rests upon the realization that Boltzmann has not dismissed the law of energy conservation itself. He argues that the second law describes the likely evolution, not a necessary result. It assumes, or at least strongly suggests, that a mechanical explanation for increasing entropy must exist. Section 2: Probability calculations and the definition of state. In this section, Boltzmann introduces his probabilistic approach to defining the state of a system. He departs from the traditional thermodynamic description, which relies on macroscopic variables like temperature and pressure, and instead focuses on the distribution of individual molecules across different energy levels. He introduces the concept of complexions, representing the number of possible microscopic arrangements corresponding to a given macroscopic state. Boltzmann then argues that the probability of a particular macroscopic state is proportional to the number of complexions associated with it. Therefore, states with a higher number of microscopic arrangements are more probable. This section is crucial as it establishes the formal link between entropy and probability. The introduction of complexions provides a discrete way to think about the continuous distribution of energy, allowing the mathematical manipulation needed to progress. The claim that probability is proportional to the number of complexions is a foundational assumption, an axiom upon which his subsequent reasoning rests. One might question its universality. Perhaps the accessibility of different microscopic arrangements varies, introducing weighting factors beyond simple counting. Section 3: Maximizing probability and the approach to equilibrium. Boltzmann then articulates his central claim that systems tend to evolve towards states with maximum probability, corresponding to thermal equilibrium. He argues that deviations from this equilibrium state are possible, but statistically improbable. This section outlines his probabilistic interpretation of the second law. Rather than entropy invariably increasing, it increases almost invariably. He avoids the term almost directly, but is strongly implicit in his discussion. This assertion is supported by the sheer number of complexions associated with equilibrium states relative to non-equilibrium states. The evaluation of this section turns to the validity of assigning probability in this manner. Boltzmann implicitly assumes ergodicity, that a system will, over time, explore all possible states consistent with its energy. This assumption remains a subtle aspect of the paper and a potential point of criticism. If the system is confined to certain regions of phase space, the calculated probabilities, seen at Section 4, the H theorem and its implications. This section, though not explicitly labelled as such in the 1875 paper, the formal H theorem appeared later, contains the seeds of Boltzmann's famous H theorem. He attempts to demonstrate mathematically that a certain quantity, which he later denotes as H, decreases monotonically over time, approaching a minimum value at equilibrium. This quantity is related to the distribution function of molecular velocities, and its decrease corresponds to an increase in entropy. This section represents Boltzmann's most ambitious effort to provide a rigorous, mechanical foundation for the second law, and to bridge the gap between microscopic dynamics and macroscopic behavior. The H theorem is a central element of Boltzmann's argument. The theorem faces serious challenges. Loschnitz paradox, for instance, highlights how time reversal symmetry contradicts such a monotonic function. Boltzmann's initial attempts to address these objections are not fully developed in this paper, pointing towards the need for continual investigation and refinement. The presentation here represents a crucial, if imperfect, first step. Section 5, Clausius' theorem and its relation to molecular kinetics. Boltzmann delves into Clausius' work, comparing and contrasting his own probabilistic approach to Clausius' more traditional thermodynamic formulation, specifically focusing on Clausius' theorem. Boltzmann argues that his kinetic theory provides a deeper, more fundamental explanation for the second law than Clausius' phenomenological description. He contends that Clausius' theorem, while empirically valid, lacks the explanatory power of his statistical interpretation. This section is significant as it situates Boltzmann's work within the broader scientific context, highlighting his ambition to replace purely macroscopic descriptions with a microscopic foundation based on molecular dynamics. The exploration of Clausius' theorem offers a valuable perspective on Boltzmann's goals. He acknowledges the practical utility of classical thermodynamics, but seeks to transcend its limitations by providing a more fundamental explanation in terms of molecular behavior. The criticism directed at Clausius' work is respectful, but insistent. While the theorem is a useful description, it cannot explain why entropy increases. Section 6, Application to ideal gases and mixtures. Boltzmann applies his theory to specific examples, focusing on ideal gases and mixtures. He demonstrates how his probabilistic approach can be used to calculate the equilibrium distribution of molecular velocities in an ideal gas, leading to the Maxwell-Boltzmann distribution. He also shows how his theory can be extended to analyze the behavior of mixtures of gases, predicting their equilibrium composition. These applications serve to illustrate the practical utility of Boltzmann's theory and to demonstrate its consistency with empirical observations. The application to ideal gases is important for demonstrating the concrete consequences of Boltzmann's theory. The derivation of the Maxwell-Boltzmann distribution provides strong evidence in favor of his statistical approach. His theory predicts measurable results that align with experimental data. This success strengthens the credibility of his interpretation of entropy. The extension to gas mixtures is itself evidence of the generality of his approach. Section 7, Objections and Counterarguments regarding perpetual motion. Boltzmann addresses potential objections to his theory, particularly those related to the possibility of perpetual motion machines of the second kind devices that violate the second law. He argues that while his theory does not absolutely preclude the possibility of such machines, it makes them exceedingly improbable. He emphasizes the statistical nature of the second law, indicating that fluctuations away from equilibrium are possible, but extremely rare. This section is crucial as it shows Boltzmann actively engaging with potential criticisms of his work. He concedes that his theory allows for the possibility of entropy decreasing, but argues that the probability of such events is vanishingly small, his response relies heavily on the sheer number of particles involved in macroscopic systems. The statistical argument weakens the force of the objections concerning perpetual motion. It is not impossible, but simply improbable. This highlights the subtle distinction between thermodynamic impossibility and statistical improbability. Section 8, reversibility and the recurrence paradox. Boltzmann directly confronts challenges related to the reversibility of microscopic dynamics. He explicitly addresses Loschand's paradox, which notes that for every trajectory leading to increased entropy, there exists a time-reversed trajectory that leads to decreased entropy. He acknowledges the validity of this point, but argues that the initial conditions required for such entropy-decreasing trajectories are extraordinarily specific and thus statistically insignificant. He also touches upon Zamilo's recurrence paradox, which posited that closed system will, after a sufficiently long time, return to a state arbitrarily close to its initial state. Boltzmann argues that while this is true in principle, the recurrence times involved are vastly longer than any realistically observable timescale. This section represents Boltzmann's most sophisticated defense of his theory against fundamental criticisms. He acknowledges the theoretical possibility of entropy decreasing, but argues that the timescales involved are so long that such events are practically irrelevant. His response hinges on the vast number of particles involved and the resulting statistical improbability of observing significant deviations from the second law. The recurrence paradox, in particular, demonstrates the limitations of applying purely mechanical arguments to macroscopic systems. Section 9, refinement of the concept of molecular disorder. Boltzmann returns to the idea of molecular disorder and refines the concept. He emphasizes that molecular disorder is not simply a matter of random arrangements, but rather a specific statistical distribution of molecular velocities and positions that maximizes the number of accessible microstates. He reiterates that a system will naturally evolve towards the state of maximal disorder, driven by the overwhelming statistical advantage of configurations with high entropy. The refinement of molecular disorder underscores the subtler aspects of Boltzmann's statistical mechanics. It establishes that it is not simply randomness, but a particular kind of randomness, dictated by the maximization of entropy. It requires a specific distribution of velocities, not merely any disorganized arrangement. This makes his theory more robust and less susceptible to overly simplistic interpretations. Section 10, implications for measurement and observation. Boltzmann delves into the implications of his theory for the processes of measurement and observation. He posits that any measurement inevitably involves interactions with a large number of molecules, leading to an increase in entropy. He suggests that this fundamental irreversibility of measurement is a consequence of the second law and that it plays a crucial, if subtle, role in our perception of the physical world. This brief discussion of measurement offers a glimpse into the philosophical implications of Boltzmann's work. He recognizes that the very act of observing a system fundamentally alters its state, contributing to the overall increase in entropy. This provides a link between the objective laws of physics and our subjective experience of reality. The notion that measurement inevitably disturbs the system is a precursor to key ideas in quantum mechanics. Section 11, further analysis of gas mixture equilibrium. Boltzmann offers a more detailed analysis of the equilibrium conditions in gas mixtures. Pushing beyond the earlier discussion, he introduces more sophisticated mathematical techniques to calculate the partial pressures and densities of different gases in a mixture, taking into account intermolecular forces and other complicating factors. He demonstrates that his theory can accurately predict the behavior of real-world gas mixtures, even in cases where ideal gas approximations are no longer valid. This deeper dive into gas mixtures provides further evidence for the practical applicability of Boltzmann's theory. It demonstrates that his approach can be extended to more complex systems, where intermolecular interactions play a significant role. It is such applications that further solidify the importance of molecular kinetics. Section 12. Critique of alternative interpretations of thermodynamics. Boltzmann offers a broad critique of alternative interpretations of thermodynamics. He dismisses approaches that rely solely on macroscopic variables, arguing that they lack the fundamental explanatory power of his statistical mechanics. He criticizes those who deny the existence of atoms and molecules, arguing that their existence is strongly supported by experimental evidence and that they are essential for understanding the microscopic basis of thermodynamics. This section demonstrates Boltzmann's unwavering commitment to the atomic hypothesis. He sees the existence of atoms as a prerequisite for a deeper understanding of thermodynamics. He actively defends this viewpoint against those who advocate for purely phenomenological approaches. The rejection of purely macroscopic viewpoints underscores his conviction that a truly fundamental understanding must be rooted in the microscopic world. Section 13. Limitations and future directions. Boltzmann acknowledges the limitations of his theory and outlined potential avenues for future research. He notes that his theory relies on several simplifying assumptions, such as the assumption of molecular chaos Stossel-Ansatz, which requires further investigation. He also points out that his theory does not fully address the problem of quantum phenomena, which would eventually require a fundamentally new approach. This brief acknowledgement of limitations displays intellectual honesty and foresight. Boltzmann recognizes that his theory is not a complete and final answer, but rather a work in progress. He identifies areas where further research is needed, including a more rigorous justification for the molecular chaos assumption. The mention of limitations regarding quantum phenomena reveals his sensitivity to the emerging challenges to classical physics. Section 14. Concluding remarks on the significance of probability. Boltzmann reiterates the central importance of probability calculations in understanding the second law of thermodynamics. He argues that the second law is not an absolute law of nature, but rather a statistical tendency that applies to macroscopic systems. He suggests that this probabilistic interpretation of the second law has profound implications for our understanding of the universe and our place within it. The concluding remarks summarize Boltzmann's core argument. The second law is fundamentally statistical. Entropy increases not because it must, but because it is overwhelmingly likely to do so. This probabilistic interpretation has far-reaching consequences, blurring the lines between determinism and randomness. This perspective challenges the traditional view of physics as a set of absolute and immutable laws. Boltzmann's 1875 paper represents a landmark achievement in the development of statistical mechanics. While some of its arguments were subsequently refined and corrected, its central insights, the connection between entropy and probability, the statistical interpretation of the second law, and the importance of molecular chaos remain fundamental to our understanding of thermodynamics. The paper's enduring significance lies not only in its scientific achievements but also in its bold attempt to reconcile microscopic dynamics with macroscopic behavior. The section Bayesian assessment reveals the meticulous logic and deep physical intuition that characterized Boltzmann's work, marking him as a pivotal figure in the history of science. More than a simple explanation of thermal equilibrium, it lays the groundwork for modern statistical physics and continues to spur intellectual debate.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.